Last section that we're going to talk about in this chapter is section 11.2. We are looking at two-way tables. So with two-way tables, there are two different tests we're going to learn. Thank you. First one that we're going to do today is a chi-square test for homogeneity, and then the one that we're going to do Monday is a chi-square test for independence. They're used in two different scenarios, but they're carried out exactly the same way. So that's why I say that they're not really the same. Well, they're not really different, but they're not the same. So what is a chi-square test for homogeneity? This test compares the distribution for one categorical variable. Thank you. That has multiple categories in multiple treatments or populations. Sorry, it'll catch up. Maybe. Okay. So, most important things here. A single categorical variable. One categorical variable. Multiple treatments or multiple populations. So like I said, there's two tests. Chi-square test for homogeneity, chi-square test for independence. And this is how you're going to differentiate which test it is. You're going to have to figure out, do I have multiple populations or only one population? And then do I have one variable or multiple variables? So a test for homogeneity, an example would be if we looked at colors, the color distribution in plain and peanut M&Ms. So if we took two populations being plain M&Ms, peanut M&Ms, and we looked at the color distribution, that would be our single variable. That would be a test for homogeneity. How is it different than a two-sample z-test for P1 minus P2? P1 minus P2 is exactly two populations. So exactly two populations in exactly two categories. So there's only two possible answers that you can give. That's what I mean by two categories.
Could you still run a chi-square test for something that you could use
Yes.
P1 minus P2 test?
Yep. We're going to look at an example.
So
for a test for difference in proportions, you could run a chi-square test.
right.
Not necessarily the other way, though.
Okay. So do people just use chi-square tests kind of for everything, or?
No, chi-square tests aren't used very often. I would say difference in proportion is more common. Okay. How do you state hypotheses for a test for homogeneity? You are going to say there is no difference in the true distribution, blah, 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 with context. So we'll do an example so that you can see more of what I mean by that. What is the evidence for the alternative? This is the same as the evidence before. You're going to have expected counts and you're going to have observed counts. So you're going to have evidence for the alternative every time your expected counts are not the same as your observed counts. What we're going to try to figure out is that difference really big or not very big? So your observed are not equal to your expected. Okay, how do you calculate expected counts? This is definitely more tedious. Okay, so you're going to have a two-way table. It's going to have a bunch of cells. In each cell, there's going to be observed values. You're going to need expected counts in each of those cells. The way that you calculate the expected value for every cell is you take the column total for that cell, you multiply it by the row total for that cell, and then you divide by the grand total. This is not on the formula sheet. So this you're going to have to memorize. Conditions, exactly the same as they were before. The one we have to be careful of is still the random. So it says we could have multiple treatments. In the case of looking at different treatments, what are we checking the random condition for?
Independence. Or checking that the wait.
Sounded like the second part was going in the right direction.
Treatments are randomized?
Yep, treatment's randomized.
What I was going to say, which is why I stopped talking.
So that would be in the case where you're giving treatments. When you're comparing two different populations or multiple populations, what does random mean? Doesn't mean that your treatments are randomized because you don't have treatments.
Random independently obtained samples.
Yeah, just random samples. Okay, formula for the chi-square test statistic. Exactly the same as it was before. Isn't that nice?
This one.
Yes.
Is it column total times row total?
Yep. Okay, degrees of freedom. You're going to take the number of rows and you're going to subtract 1. You're going to multiply by the number of columns, subtract 1. Can you do this on the calculator? Yes, you can. Good news, it's on every calculator. So regardless of if you have the new or the old calculator, every calculator can do this one. Remember how I said there's the chi-square test and the chi-square goodness of fit? Well, we're not doing the calculator yet. We're going to do an example. I don't even have numbers for you to put into a calculator yet. Okay, ready to do an example? Okay, great. We're going to do the example on the next page. It's about background music, I think. Inspired by the background music example, a student randomly assigned 20 volunteers to get a red survey, 20 volunteers to get a blue survey, and 20 volunteers to get a control survey. The first 3 questions in each survey were the same, but the 4th and 5th questions were different. For example, the 4th question on the red survey was, when you think of the color red, what do you think about? On the blue survey, the question replaced red with blue. On the control survey, the questions were not about color. As a reward, the student let each volunteer choose a chocolate candy in a red wrapper or a chocolate candy in a blue wrapper. Do these data provide convincing evidence at the alpha equals 0.05 level that planting thoughts about color affects color choice? Okay, first of all, do we get what's going on in the question? Okay, so everyone gets a survey. It's either red, blue, or control, so white, let's say. They get asked the same 3 questions, and then the people with the red survey get asked, what do you think about red? People with blue survey, what do you think about blue? And the white survey, they just get asked a different question. And what we want to know is, if you have the blue survey and you go to pick a candy, are you more likely to maybe choose blue than if you just had a white survey? With me now? Okay, great. Are we comparing multiple populations here or multiple treatments? Treatments. And then the single categorical variable would be, bless you, the choice of the wrapper color. So that's why it's a chi-square test for homogeneity. Single variable, color choice, multiple treatments. State step. We okay if I do not use complete sentences? Okay, still upper-tailed. Like we said, chi-square is always upper-tailed. It's upper-tailed. It's a chi-square test for homogeneity. Of course, give your alpha. Alpha is 0.05. Chi-square always needs degrees of freedom. So in your two-way table, the number of rows, so 2 rows minus 1, times the number of columns minus 1. You're not looking at the total column, though, bless you. Just the columns and rows that have data in them. So in this case, 2 degrees of freedom. I don't care that you show this. If you just want to say degrees of freedom equals 2, that's fine.
Does that mean you can get like fractional degrees of freedom?
No. How would you get a fraction?
Oh wait, sorry, no, I'm thinking. I'm not thinking.
You're thinking expected value?
I was just not thinking.
Okay, cool. Good talk. Alex?
Can you write the symbol for chi-squared instead of chi-squared?
Yeah, like I did? Yeah. Yeah, people generally don't write out chi-squared. Okay, you want to hear the good news about this test?
Yes.
No parameters to define at all. We can just jump right to the null. That's pretty good, right? Okay.
What's that?
Okay, so the null. In your null, you're going to assume that there's no difference in the distributions. So our null is going to be, there's no difference in the distributions of candy color choice for those who get the red, blue, or control surveys. So my 3 distributions that I'm comparing are by color of survey. The red survey distribution, the blue survey distribution, the control survey distribution. Please make sure that you are using present tense. I've been saying that over and over again, and some of you keep forgetting. So alternative is going to be, there is a difference. There is a difference in the true distributions of color choice for people like these who get the red, blue, or control surveys. Why do I have to say for people like these? Because we have volunteers. Yes, this is not a random sample, so we don't get to generalize to everyone. We only get to make a conclusion about our volunteers or people like them. So the plan step is shorter, isn't it? Kind of, maybe. Okay, cool. Plan step. What does random mean in this case? Yeah, treatments randomized. So I'm going to say treatments were randomized. And that's stated. Second assumption, just like goodness of fit test, you have to have a large sample. So all of your expected counts have to be at least 5. Like goodness of fit, I expect to see a formula. So for expected, you're going to do the row total times the column total divided by the grand total. Okay, I tend to then put my expected values in a table similar to the table that's above. So the table above, ignoring the totals, has 2 rows and 3 columns. So this is what I tend to do, and I think it makes the most sense. And then label it similarly. You don't have to write out red, blue, control, but at least put something that I can follow your reasoning. Okay, like before, you have to show one substitution. I don't care which one. Draw me an arrow to whichever one you choose. So the expected value for this cell. If we go up to the table, it's going to be the row total for, so this is the cell I'm looking at. The row total for that cell, which is 26. The column total, which is 20. So this is going to be 20 times 26, and then the grand total is 60. That gives you an expected value of 8.67. Now, do you notice that all of the expected values in the first row are going to be the same? Look at your table. Okay, why are they the same? Right, because the columns are the same. So that won't always be the case, but in this case, these expected values are all 8.67. If you were to do this cell, the row total is 34, the column total is 20, and then divided by the grand total. That gives you 11.33. And then show me that they all are in fact greater than or equal to 5. Do we have to do the 10% rule? No, why not? No sampling. So we have all volunteers. Okay, now to actually carry out the test. So first thing, you're going to write the formula like you did before. You're going to do your substitution. So observed minus expected. The first observed in the table is 13. So I'm going to do 13 minus 8.67 squared over 8.67 plus ... all the way to the last one, which is 12 minus 11.33 squared over 11.33. Okay, this is different on the calculator. So this one is actually pretty different from what you've done before. The calculator is going to need the observed values and it's going to need the expected values. Let's do it like this. Okay. Both your observed and your expected values are going to go into a matrix. So you're going to go to second matrix and go over to edit. Do the observed first. So this matrix here, again, if we're only looking at our data, is 2 by 3. And then you're going to put in the observed values. So the 13, 5, 8, etc. Okay, when you're ready, then go to matrix B, and you're going to put in the expected values. So that's, again, 2 by 3. They should have the same dimensions. Ideally, you wouldn't use rounded values, but we will now just for time's sake. Okay, let's carry out the test then. You're going to go to stat, you're going to go to tests, and then you're going to go to chi-square test. Not the goodness of fit, but chi-square test. Chi-square test is always for homogeneity and independence, which we'll do Monday. If you check that, the observed we put in matrix A, the expected we put in matrix B. If you hit calculate, it'll give you the chi-square value, the p-value. It'll also give you the degrees of freedom too. So for work then, I expect to see, I'm looking for the probability that chi-square is greater than or equal to 6.65, which is about 0.0359. I do expect to see a figure, so you're going to have to go back and do the same test again, except choosing draw. Sorry, I always have these lines on here that I don't mean to have. So just draw the figure the way it looks. I can't see any shading on mine. Do you guys have shading on yours? No, okay. So then just tell me this is where chi-square equals 6.65. Okay. Questions on the calculator? No. Great. We are going to write a full conclusion since we haven't done that in a while for chi-square, at least in class. So you're going to show 0.0359 is less than 0.05. So we are going to reject. So based on my analysis, I reject the null. And instead believe there is a difference in the two true distributions of color choice for people like these who get the red, blue, and control surveys. Okay, what does that mean practically? Like if you were talking to someone who wasn't in statistics?
You believe this
Matters.
What?
The color of the survey matters.
Yeah, the color of the survey somehow affects the wrapper of the candy that people are choosing. Okay, for the p-value. Have I told you about an experiment like this before? About color? No? I'll tell you again, and if I said it, you can just stop me. I had a professor when I was in grad school taking a statistics course who was a statistician, and she worked for State Farm, I think. I didn't tell you this? I did, right?
I like the
Wow.
baby.
What?
Okay, I'll tell you again. So she worked for State Farm, and so part of her job was to run some analysis on their website. And so one of the experiments that she did is if you ever look up your insurance, you can go to a website and click a button that says, get a quote. And so she would randomly assign every person that came to the site a color for that button, and they analyzed which color people would click on most frequently.
What color was it?
I don't know. She didn't tell us. Sorry to tell you. Okay, p-value. So the probability of obtaining the observed distribution or one more extreme assuming no difference in distributions of color choice based on survey colors is 0.0359. So just the probability of getting what we got, assuming the null is true, is 0.0359. Okay, questions? No. Okay, or I guess the second question. Do a follow-up analysis for the previous example. Do you know what a follow-up analysis means for chi-square? No. Okay. We recognize from this formula that there's going to be a chi-square for each of these categories, right? And that they get summed up. With me? Okay, so when I ask you, do a follow-up analysis, I want to know which chi-square value is going to be the biggest. So, if we look out of the first row where they're all the same, the expected values, Which chi-square value is going to be the smallest?
8.
This one, right? The observed and the expected are really, really close. Okay. Which one will be the largest? The first one, the 13 away from 8.67, that'll be the largest. What about the second row? Which one's going to be the largest? Maybe 15, maybe 7. So what you're going to want to do is calculate all three of those. So let's do those and find out which one is the biggest. So I'm going to start with the 13 in the first row, because we said that one would be the biggest in the first row. So we're going to do 13 minus 8.67 squared divided by 8.67. So that is the chi-square value for that first observation, the one that's right here. In the second row, we said either 7 or 15 would be the biggest. So then you're going to do the 7 one. So that chi-square value is a little bit smaller than the one we did previously. And then you're going to do that 15. So it looks like this one right here was our winner. So that contributed most to our chi-square test statistic. So here's what I would say in words. The red candy chosen in the red survey group contributed most to the chi-square statistic. And I would give the chi-square value, which was 2.16. So that is the one group that contributed most to us rejecting the null. Okay. How do we feel about chi-square test for homogeneity?
When do you do the follow-up analysis?
When you're asked.
Okay.
So you don't ever have to do this unless you're asked. I've seen it asked maybe once. So you should know how to, but it doesn't come up very often.